In the previous lecture, we had started looking at the notion of partial derivatives and how do you compute partial derivatives using chain rule for composite functions. So, let us look at some examples of computing partial derivatives using chain rule. So, the first example we look at is the example f x y, which is given by x square plus y square for x and y belonging to R 2. So, let us find out why it is where this is a function of two variables, and let us assume x itself is a function of a variable t given by x t is equal to e raised to power t. So, keep in mind it is exponential function e raised to power t, where e is a number. Okay. We had looked at this function in the first lecture or second lecture, and y of t is equal to t for t belonging to R. So, x is a function of t and f is a function of x and y, y is also a function of t. So, what will be f as a function of t? We can actually put the values of f values of x in this formula. So, that will give you x square, that is e raised to power 2 plus t square. So, f actually becomes a function of one variable, and we can compute the derivative as if it is a function of one variable. But we want to illustrate this as a example of chain rule. So, let us look at w t as a function f of x t comma y t. So, this gives us the value f is a function of x and y, and x is a function of t and y is a function of t. So, by chain rule, what will be the derivative of w with respect to t? It is a partial derivative of f with respect to x into derivative of x, that is dx by dt, plus derivative of y f with respect to the variable y into dy by dt. So, partial derivative of f with respect to x, that we get from this equation. So, that is 2 x, y is kept constant. So, that is 2 x. So, and 2 x, x is equal to e raised to power t. So, you get the first term as 2 x 2 into e raised to power t into dx by dt, but x t is equal to e raised to power t. So, its derivative is dx by dt, that is e raised to power t itself. If you recall, we had mentioned that for the exponential function, derivative is itself, plus the contribution with respect to the second variable now. So, that will be partial derivative of f with respect to y into dy by dt. So, partial derivative of y with respect of f with respect to y is 2 y, and y is equal to t. So, that is 2 t into dy by dt. So, dy by dt is equal to 1. So, that is only 2 t. So, using chain rule, the derivative of w with respect to t is this expression, which you can simplify into 2 into 2 e raised to power t plus t. So, that is okay. Let us look at the function same function f x y is equal to x square plus y square, but here x now is a function of two variables s and t. X of s t is equal to s square minus t square, and y of s t is 2 times s t. So, it is the same function of two variables, is same as before x square plus y square, but now x is a function of two variables t and s. So, s square minus t square, and y also is a function of two variables s and t. So, if you like, you can put these values in x square plus y square, and you will get f as a function composite function as a function of two variables, but the formula will look quite complicated. So, let us try to use chain rule to find the partial derivative of this. So, f is a function of two variables x and y, x itself is a function of two variables s and t, and y also is a function of two variables s and t. So, partial derivative of the composite function. So, what will be the composite function? F of x s t comma y s t. So, we can compute the partial derivative of that function. So, the function is g s t, which is f of x t x s t comma y s t s of t belonging to R. So, g is a function of two variables and s, right, g is a function of two variables s and t. However, this comes as a composite function f of x s t comma y s t. So, g as a function of two variables will have partial derivative with respect to s and with respect to t. So, how do you find that? So, partial derivative of g with respect to s, to compute that we will look at. So, it will be two terms coming, partial derivative of f with respect to x, and if you are differentiating with respect to s, then the partial derivative of x with respect to s. So, that will be the first term plus partial derivative of f with respect to y multiplied by partial derivative of y with respect to s. So, that will be the partial derivative of g with respect to s. So, let us compute that. So, partial derivative of g with respect to s will be partial derivative of f with respect to partial derivative of f with respect to x into the derivative of partial derivative of x with respect to s. So, that gives you this term plus the second term, that is the partial derivative of f with respect to y into the partial derivative of y with respect to s. So, that is the second term. So, similarly, we can find the partial derivative of g with respect to t being, first look at partial derivative of f with respect to t into the partial derivative of y with respect to t plus partial derivative of f with respect to y in terms of partial derivative of y with respect to t, and all are put in terms of s and t. So, that your answer eventually is in terms of s and t. So, this is how you apply chain rule and compute the partial derivative of composite functions using what are called chain rules. Let us go to slightly next concept. See, in functions of one variable, we said that if the first derivative, the derivative of a function exists at every point in the domain, then we can ask whether the function is differentiable again, and if it is so, we will get the what is called the second derivative, and similarly the third order derivative and so on. Similarly, partial derivatives are functions of one variable only. So, if the partial derivative of a function of two variables, say f x y, if the partial derivative of f with respect to x exists at all points, then it is a function of two variables again, and one can ask what are its partial derivatives. So, partial derivative f of x will have two partial derivatives again, differentiating f of x with respect to x and then differentiating this with respect to y, or differentiating it with respect to x again itself. So, each partial derivative will give you two more partial derivatives of higher order depending on the function. So, let us write this so that we are able to use them. So, the first one is f x x, which is also written as partial derivative with a power 2 here. So, del square f divided by del x square. So, this is how you read this. So, it is del square f del x square, or it is a second order partial derivative of f with respect to x and x. So, what is this? You take the function, find its partial derivative with respect to x, and then again find its partial derivative with respect to x. So, this is partial derivative of x twice, you can call it. So, partial derivative of f with respect to x, that gives you a function, find its partial derivative with respect to x. The other possibility is you look at similarly with respect to y. So, look at the partial derivative of f with respect to y. So, that gives you one partial derivative function, right. This is the partial derivative of f with respect to y, and that may be differentiable with respect to y again. So, we can find the partial derivative of this function. This is a function of two variables, keep in mind. Partial derivative of f with respect to x is a function of two variables, as well as the partial derivative of y f with respect to y is again a function of two variables, if we assume it to be differentiable everywhere with respect to the variable. So, then if the partial derivative of this function, which is a function of two variables with respect to y exists, then this is called the second order partial derivative of f with respect to y, or read as del square f by del y square, or f y y, or simply saying it is the second order partial derivative of f with respect to y. Other possibilities are this function exists, for example, partial derivative of f with respect to x exists, but we instead of asking partial derivative of that with respect to x again, we can ask what is the partial derivative of this with respect to y, that may exist. So, that gives you another possibility that the partial derivative of f with respect to x, its partial derivative with respect to the variable y. So, that is written as del square f del y del x. So, note that here x is, so as if the bracket is removed and this del is multiplied and called del square and del y del x, right. So, this is only shorthand notation. So, you should read it as it is a second order, 2 indicates the order, f of the function f. So, partial derivative, second order partial derivative of f. What is the two orders? First with respect to x and then with respect to y. So, you are going to read from right to left, while as in if you can also write it as f of x y, there you will read it as from left to right. So, you will be reading as x first and then with respect to y. So, keep in mind whether if this notation is used, this is first find the partial derivative of f with respect to x and then with respect to y, right. So, that is going this. So, this lower suffix is going from left to right, whereas here in the denominator, if you think it is a denominator, it is going from right to left. So, this is the second order partial derivative of the function f, where the first you differentiate with respect to x and then differentiate with respect to the variable y. Similarly, there will be a partial derivative what is denoted by y x, that means you first differentiate with respect to y and then with respect to x, also called partial second order partial of f by del square f divided by del x del y, or second order partial derivative of f with respect to y and then with respect to x. So, that is the order here, that is left to right and it is right to left. You take the function partial derivative of f with respect to y first and then you take its partial derivative with respect to x. So, there are 4 partial derivatives available, second order partial derivatives for a function of 2 variables. All of them may not exist, some of them may exist, but these are the possibilities of. So, these are called 4 second order partial derivatives of a function of 2 variable. These f x y and f y x, they are called the mixed second order partial derivatives, because the variables x and y are mixed here. So, this is called f x x, f y y. So, they are pure second order derivatives, and these are called the mixed second order partial derivatives. In general, f x y is not equal to f y x. So, caution should be taken that in general for a function of 2 variables, the 2 mixed second order partial derivatives are not equal. So, there are sufficient conditions which ensure that when they will be equal. We will not go into those conditions, however, we will assume that for our purpose they are equal. So, those conditions are satisfied. So, these are called the higher order partial derivatives. So, they correspond to something like second order derivatives of a function of one variable. We are defining them because they find applications in economics, commerce and management. So, let us look at one example. Let us recall the Cobb-Douglas function, which was defined as q is equal to q k l, a into l raised to power alpha. Once again, this is l is a typo, it should be k raised to power beta, where a, alpha and beta are positive constants. K is the capital and l is the labor input. For this function, just now we saw today that the marginal of the product of labor q l is a partial derivative of q with respect to l was obtained as this, and the partial marginal of q with respect to k was today we got as beta q by k in the previous lecture. So, these are the marginals of the Cobb-Douglas function which we obtained. So, let us look at the second order, both the marginals are positive, that we know. So, let us look at the second order for this. So, q l l will be the second order partial derivative of q with respect to l. So, that we can differentiate by looking at this one, alpha q by l. So, it will be l square. So, by the quotient rule, So, this will be L square, this will go up. So, alpha times L into derivative of q with respect to L minus the q times alpha q into derivative of L, that is 1. So, let us put these values. So, that is equal to, so L into derivative of q with respect to L minus q into derivative of L, that is q. So, if we simplify, that is alpha into alpha minus 1 into q divided by L square. So, that is the simplification we get. Similarly, the second order partial derivative of q with respect to k is partial derivative of. So, take the first order partial derivative, that is we obtained in the previous. So, that is the partial derivative. So, this function, this is the first order partial derivative, second order partial derivative using the quotient rule. So, k square in the denominator, numerator will be beta times k into derivative of q with respect to k minus q times derivative of k, that is equal to 1. So, that gives us the second expression, namely the second order partial derivative of q with respect to k is beta into beta minus 1 divided by k square into q. So, these two expressions are the marginals, they are the derivatives of marginals. So, these will tell us how does the marginals change, right, what kind of functions the marginals are there. So, keep in mind that alpha and beta are positive and q and L are positive. So, if alpha is between 0 and 1 and beta also is between 0 and 1, so that will give us 1. So, normally in production in a production function, we require that the values of inputs increase, the marginal should decline. If there is an increase in the values of the product function, right, then that means if the inputs increase, marginal should decline. So, that is a normal principle, guiding principle for economic models. That means, we want QLL and QKK to be decreasing functions. For them to be decreasing functions, we should have alpha to be less than 1 and beta should be less than 1. So, that is the reason one normally if you want this property to be true, that the functions, their derivatives are derivative of the marginals, these are the second order partial derivatives. If they are negative, then that condition will be true when alpha and beta both are less than 1. They are non-negative quantities. So, they should be between alpha between 0 and 1. So, in Cobb-Douglas model, normally one says alpha and beta are positive constants and they are between 0 and 1. So, that is the basic assumption taken in Cobb-Douglas model, and the reason is as indicated here, this basic principle of economics. So, now what we will be doing, we will start looking at the notion of local maxima and local minima for functions of two variables. If you recall, for functions of one variable, how we looked at the notion of local maxima and minima, we first obtained a necessary condition, namely that if at a point a function has local maxima or a local minima, then the derivative and the derivative at that point exists, then the derivative should be equal to 0. So, that gave us that necessary condition gave us the possible points where the local maxima or minima can occur. And then we had the various tests, the continuity test, the first derivative test and the second derivative test to analyze whether those possible candidates for local maxima or minima are actually local maxima or minima for the function or not. So, they were the sufficient conditions. So, we had necessary conditions for local maxima minima and sufficient conditions for local maxima minima. The same process we are going to follow for functions of two variables. So, first we will define what is called the local maxima and local minima for a function of two variables, and then give necessary conditions for a function of two variables. If it has a local maxima and or a local minima at a point, then what are the conditions, and then we will look at the sufficient conditions to analyze those possible candidates where the function can have local maxima or local minima. So, let us look at the definitions. So, the first definition says, for a function of two variables with a domain D, D is a subset of R2, a point x0, y0 is called a point of local maximum. So, if there is a ball, this B delta x 0 y 0 is nothing but a ball centered at x 0 y 0 of radius delta. That means, this is a set of all points at a distance maximum of delta. So, let me just explain because we have not really explained this very well in the beginning. So, for the in the plane, so if I take a point x 0 y 0, then what is ball centered at x 0 y 0 of radius delta. So, this is nothing but this is a set of all points x and y belonging to R 2 such that the distance between x 0 y 0 and x y is less than delta. So, what is the distance? So, the distance is x minus x 0 square plus y minus y 0 square, this is less than delta. So, this is a set of all points, and in the picture, so if this is the point x 0 y 0, then these points are nothing but the points which are at a distance of delta. So, that means, at a distance of delta you are looking at, but strictly less than delta. So, you will be looking at all points in the disk, but minus the boundary is not going to be included. So, all points inside, that is the ball, that is a ball. So, we say it is a ball of radius delta at, so at the point x 0 y 0. Because we are not including the boundary, one normally actually qualifies open ball of radius delta. This is also sometimes called the delta neighborhood, of the point x 0 y 0. So, recall in a function of one variable, we defined the neighborhoods by the open intervals centered at that point. Here B of x 0 y 0 is an open ball in the plane centered at x 0 y 0. So, what we are saying is a point of local maxima at the point x 0 y 0, if there is a neighborhood of that point in the domain of course, such that at all these points x y, the value of the function is the largest. So, f of x 0 y 0 is bigger than f of x y for all points in the delta neighborhood of the point x 0 y 0. So, in this case we say it is a point of local maximum. So, locally, so what does locally mean? So, in an open neighborhood of that point x 0 y 0, in the domain the value is the largest. So, locally the value is the largest, and similarly we say it is a point of local, in this case we say that this value of the function, the point is called the point of local maximum, and the value of the function at that point is called the local maximum of the function. One can define similarly the point of local minimum at x 0 y 0 to be that point such that there is a neighborhood delta bigger than 0 with the property that the value at the point x 0 y 0 is smallest for all points in that neighborhood, open ball around the point x 0 y 0. Then you say it is the local minimum, and the value of the function at that point is called the local minimum. That point is called the point of local minimum. So, you can have look at some examples. If I look at the function f x y is equal to minus of x square y square, then we had tried to visualize the graphs of these functions. They are surfaces. This will look like a inverted cup, and the negative, that means the surface is going to lie below the x y plane. So, the point x 0 y 0, the point 0 0 is going to be a point of local maximum, the value will be 0 0. So, the point 0 0 is going to be a point of local maximum, and the value 0 is the local maximum for such a function. If I just invert it, so the function becomes f x y is equal to x square plus y square for x y belonging to this. Then we get that the point 0 0 is a point of local minimum, and the value at 0 0 is the local minimum for the function. So, this is simple examples of local maximum and local minimum for the functions. Like functions of one variable, we have the following necessary condition for local maximum and local minimum. So, let us write this as a theorem, that if f is a function which is defined in some open domain in R 2, a function of two variables, if both the partial derivatives exist and f has a local maximum or a local minimum at the point x 0 y 0, either of it, then the partial derivatives of f with respect to x and partial derivative of y with respect to f with respect to y at that point must be 0. So, what we are saying is, if a point x 0 y 0 is a point of local maximum or a local minimum for the function and the partial derivative exists at that point, then they must be equal to 0, which is perfectly similar to the function of one variable. If local maximum or a local minimum for a function of one variable exists and if the function is differentiable, then the derivative must be equal to 0. So, that is a necessary condition that we get for a function of two variables to be a point of local maximum or local minimum. But keep in mind that if we look at the, for example, the function square root of x square plus y square, this function does not have local maximum, does not have partial derivatives at the point 0 0. That you can easily check, because this ratio f of x 0 f of y 0 divided by x will be equal to mod x by x, which is that limit does not exist at the point 0 0. So, for this function the partial derivatives do not exist, but the function has got a local minimum at the point 0 0. So, keep in mind the function can have a local maximum or a local minimum without partial existence of partial derivatives. Is a point of local minimum without. So, thus the condition in the theorem is only a necessary, but not a sufficient condition. So, let us define what is called a critical point. So, like in one variable, an interior point in the domain of the function will be called a critical point if either both f of x and f y exist and are equal to 0, and second possibility is one or both of them do not exist, like in one variable derivative may not exist, or the points where there could be the boundary points, the third one we are not listed here, we should list that also. So, those also could be the points of. So, these are the interior points. So, okay. So, for interior points there are only two possibilities: partial derivative exists and are equal to 0, or either or both of the partial derivatives do not exist. So, keep in mind this is for the interior points. Okay. So, as a corollary of this, we will get that a function can have a local maxima minima can occur only at the critical points or possibly at the boundary points of the domain. Like in function of one variable, the critical points and the boundary points together give the possible candidates for the function to have a local maxima or minima. So, like in one variable, we gave sufficient conditions for the possible points to be local maxima or minima. Same we will do it for functions of two variables in the next lecture. So, we will continue our study of points of local maxima minima for functions of two variables in the next lecture. Thank you.